let's start chapter 20, quiz 1, which is a homework problem. So not only are you going to get this quiz correct, but sometime today or sometime tomorrow, you should go in and solve the chapter 20 homework problem that corresponds exactly to this. Just, just that. That's really not my idea. I'm just sort of pirating that from another student who always, she was Rebecca. Rebecca was always doing that and always doing well. An ice cube. Let's draw an ice cube. Here is an ice cube sitting in a lake. Okay, ice cube. There's an ice cube. Ice cube sitting in a lake. And a 26-gram ice cube at negative 89 degrees Celsius. And I know kind of instinctively, I know I'm going to convert this to, I know I'm going to convert from degrees Celsius to Kelvin, just because everything we do here, everything that's based on the ideal gas law, everything that's based on entropy is Kelvin based. So I have a 26-gram ice cube. This is 26 grams or 0.026 kilograms. That's the mass of my ice cube. It's sitting there at a very cold temperature, so it's well below its freezing point. So the initial temperature for the ice is negative 89 degrees Celsius. And you would know instinctively that if you throw an ice cube into a lake, of course, heat is going to flow from the lake into the ice cube. So this needs to be added. You know that instinctively, you know that experientially, and now you can actually say, well, apparently I've already known about the second law. This is really the second law. The second law of thermodynamics says heat will always naturally flow from hot to cold. And in this case, the lake is the hot reservoir. So the lake is sitting here, T initial for the lake is sitting there at 80 degrees Celsius, pretty warm. It's this lake is quite warm, 80 degrees Celsius. The mass, I don't know the mass of the lake. Okay, so that's good. So if you walk up to this lake and you throw this ice cube into this lake, it's going to melt, right? And then it's going to melt and things are going to happen. And the question is, what's the change in entropy of the system? What is the change in entropy of the cube lake system? That's what we're after. And I keep not doing that. Okay. Well, fine. That's what we're doing. As the cube comes to thermal equilibrium with the lake, and then we know the specific heat of ice, and we know the specific heat of water, although that's not given, but we do know what that is. It's in your lecture notes. All right, so let us begin. Number one. Well, ice warms up. So the first stage that this ice cube is, the system is going to go through, heat will flow into the ice cube will warm up, and I guess that's, ice will warm up, ice warms up, then melts, then warms up again. The melted ice, which is water at that point, that melted ice water warms up again. So that's the first thing that comes to my mind. In terms of a narrative, and your goal is to provide explanatory comments that kind of read like a narrative. Ice warms up, then melts, then warms up again. Entropy, I'm going to say the change in entropy. This is what you're being asked to solve. Calculate the change in entropy. So you're not calculating S. S is entropy. It's a state variable. State variables only care what their value is. They have no memory of the path that led them to their current value. I'm not after entropy. I'm after the change in entropy. And I can see because I have a system, this word really kind of sticks with me. Calculate the change in entropy of the cube lake system. So I'm not focusing on the cube. I'm not focusing on the lake. I'm focusing on both. So that's what I'm going to say. Whatever the change in entropy is for the ice cube, I'll do C for cube, plus the change in entropy for the lake. That's the total. I'll put T for total. So the total change in the universe's entropy is going to be a combination of the changes in the ice's entropy along with the lake's entropy. So that's how I'm still in setup mode. Okay, look at ice. Look at ice warming up. Let's look at the ice warming up. Again, it starts very cold, negative 89 degrees Celsius, which is quite cold. So the first thing that's going to happen is the ice will warm up. So let's just focus in on that. The change in entropy for the cube during this warming up process is defined, triple equal sign, is defined as dq reversible all over T. So just a little sidebar comment. I'm writing this down. If this is the first time you're seeing this expression, that's okay. No, no harm done, no permanent damage. All I'm saying, if this is the first time you're seeing this expression, you are not getting, you are at a disadvantage. You're just not going to get out of this conversation what you could get out if you have some familiarity with this. So just keep that in mind. The goal is to come armed with watching those lecture videos at least once before this point in time. So, well, let's do one of the transfer functions. This is going to equal dq. This is ice warming up. So I'm thinking, let me back up. I'm thinking this, Q, I better do another number 5. Maybe I'll keep going here. So what is the integral? I can't solve that integral. So I'm saying for warming ice, I can say this. For warming ice, ... I know Q equals MC delta T. In general, for warming ice, Q equals MC delta T, the specific heat capacity. And specifically, I'm going to say for the cube, I'm going to subscript C's like that. And that becomes, let's see, it's the mass of, well, you know what? I'm going to leave it like that. And then I'm going to deltaize this. Deltaize. That's I'm going to differentiate this, or I just call deltaize this. So I'm going to say, if I just take the derivative of number 6, that's how I'm going to get dq subscript C referring to the cube equals MC C subscript C. And I'm going from delta T to dt. So this expression that I'm just writing down right here, this is exactly like this. This here is just the differential version. Okay, so, and I'm really kind of recapping some of what was in the green sheets, but not everything, not the deep story. All right, so here goes. Rewrite number 4. So rewrite number 4, and this is what I have. I have the change in entropy for that cube during this warming phase can be stated as integral of MC C subscript C d Tc all over T. And my limits of integration would be from some initial temperature to some final temperature. So this is an integral you can solve. You can see the constants. The constants come out here. M is the constant. That's the mass of the ice cube. C subscript C is a constant. That's the specific heat capacity for the ice cube. So now we can actually keep going and say change in the cube's entropy is going to equal the mass of that cube, the specific heat capacity of ice, which is given to us as 2220, natural log of T final all over T initial. Okay, let's get an answer on that. And then make sure you store this in your calculator. This is a very intermediate value, but let's see. Let's do a sanity check. Do I know the mass of the ice? Yes, it's 26 grams or 0.026 kilograms. So I'm going to use 0.026 kilograms. Do I know the specific heat capacity for water in the solid state, also known as ice? I do. It's 2220. Do the dimensional analysis. Do I know the final temperature? I do, but convert. Once again, I am going to convert from, oh, that's interesting. We should talk about this. T sub F equals, that's a good question. The ice is warming up to the melting point. Okay, so T sub F is going to be the melting point of ice, which is 0 degrees Celsius. And I know I need to convert from Celsius to Kelvin. And 0 degrees Celsius is 273.15 Kelvin. The initial temperature for this ice was negative 89 degrees Celsius. And when I convert that, I just add 273.15. So 273.15. I think Wiley Plus might just use 273. So if we're off a little bit, that would be one place to look. I'm using 273.15. I believe Wiley Plus uses 273, but I can't remember for sure. So just saying. Negative 89, and this ice cube is going to start off at a cold negative 89 degrees Celsius. I'm going to add 273.15. So I'm going to end up at 184.15 Kelvin. Okay, so let's get an answer for the change in entropy for the ice as it warms up. All right. 0.026 times 2220 times natural log of that numerator divided by that denominator. And I get an answer. Number 9. The change in entropy for the ice cube as it warms is 22.75 joules per Kelvin. We should do the dimensional analysis. I would have, I'm going to have kilograms times specific heat capacity, and specific heat capacity is joules per kilogram Kelvin. And then I'm going to multiply that by, that's it, because the natural log is just a number. So once again, from a dimensional analysis point of view, mass is given in terms of kilograms. Specific heat capacity is given in terms of joules per kilogram Kelvin. That's how I do end up with joules per Kelvin. So that's good. I'm just going to repeat this one more time just to be paranoid. 0.026 times 2220 times natural log of that final temperature, which is 273.15 divided by the initial temperature, which is 184.15. Okay, store alpha A. Let's put that, and then let's move on. So this is for sure going to live in memory location A. That's the warming phase. And now, once the ice cube warms up to its melting point, it's going to melt. Look at ice cube melting. That's our next step. Number 11. So for the ice cube melting, I'm going to put change in entropy for that ice cube melting. Okay, it is once again, change in entropy is defined as dq reversible. And the lecture, the green sheet lecture, talked a lot about what is a reversible process versus what is not a reversible process. So that should be familiar to you. All right, so for a melting ice, for a phase change, this is a phase change. This was talked about in the green sheets. For a phase change, I can do this. For a phase change, delta T equals 0. This was that diagram that we spent some amount of time on in chapter 18 where we said, okay, if I keep adding heat, like let's say if I have an ice cube, well, the ice cube is warming up and then it's melting and then it's warming up again and then it's vaporizing. So, and these flatline portions should have meaning to you. During this flatline portion and during this flatline portion, heat continues to enter the ice, but the temperature doesn't increase because the bonds are being broken. All of the heat being added to the ice during this phase is not spent on increasing temperature. It's spent on breaking the bonds and converting from solid ice to liquid water. So that's why I'm saying during this phase change process, there's no change in temperature. Temperature is constant. So I can use this transfer function, delta S for, again, the cube, while it's phase changing. I'm going to write it like this. It's 1 over T because T is constant. So T is not part of the integrand. It comes out just like any other constant would come out, times the integral of dq. And in this case, here's my expression for dq. I'm just going to say, well, the integral of, what is the integral of dq? The answer is q all over T. So that's it. This is what I'm going to use for my melting ice. ML subscript F all over T. That's the answer. And let's talk about it. This is the mass of my ice cube. So it's still for me 0.026 kilograms. So that number is the same. L subscript F, this is the latent heat of fusion. It's a material constant. We look it up in the table. It will be given to you. You don't have to have it memorized. And once again, T is a constant. This is the temperature at which this phase change is occurring. So if I take this another step, number 13, all right, so I have the change in entropy for this cube as it's melting is going to equal the mass. I'll use some numbers here. My mass is 0.026 kilograms times the latent heat of fusion for water. So let me get out the old textbook and let's take a look at the latent heat of fusion for water. And I think we can use this for some other lookups too. This is chapter 18, I think it was. All right, so I'll put this on your screen and we can all look at it. It's here in chapter 18, I think. There it is. Okay, so let me. Okay, so according to this lookup table, some heats of transformation, and I'm looking specifically at the latent heat of fusion. Fusion refers to the phase change between solid and liquid. This ice could go from solid ice to liquid water, or it could go from liquid water to solid ice. One way or the other, we are thinking in terms of latent heat of fusion, which according to this table is 333 kilojoules per kilogram. So let's use that. 333 kilojoules per kilogram. So step 13 is coming directly from step 12. Let's write down 333 E3. It's not natural log base E. It's 333 times 10 to the third joules per kilogram. And all of this is going to be over T right here. So the question right now is, what is the temperature? And the more complete question is, what is this temperature right here? What is the temperature during which ice undergoes a phase change from solid to liquid? That happens at the freezing point. That's always the answer. That happens at the freezing point. And in the case of ice and water, the freezing point of water is 273.15 Kelvin. So let's put that into our calculator and store it, making sure, I need to have all this stuff stored. So 0.026 times 333 E3 divided by 273.15. I get 31 and some change. So this is, and again, you guys, you would be doing all of us a favor if you shout out some questions or corrections just to find out, just to let me know what mistakes I'm making. Joules per Kelvin. So dimensionally, I'm feeling good. Joules per Kelvin is what I'm expecting. That is the unit for entropy. I'm going to put this in calculator memory location B. And I'll redo this. This is 0.026 times 333,000 divided by 273.15. Is that the same as what I had before? The answer is no, it's not. Let me double check something. Darn it. 0.026 times 333,123 divided by, okay, store alpha B. That time for sure. I accidentally put it in memory location A, so I'm going to redo step 8 just for a second. 0.026 times 2220 times natural log of 273.15 divided by 184.15 equals that number. Okay, now I'm back to normality. All right, so we looked at the ice warming up. Look at the ice warming up. We did that. Look at the ice melting. We did that. The last phase here, well, not the last phase, but the next phase is, let's look at the ice water warming up. Look at ice water, the melted ice water. Look at melted ice water warming up. It's going to warming up to lake's temperature. The lake is so large that you could make a case. If I throw an ice cube in a lake, the lake's going to cool down. And technically that's probably true, but the difference between the volume of water in a lake and the volume in an ice cube is so large that we consider the temperature of the ice to be, we consider the temperature of the lake to be unchanged. In fact, it says that here, I think. Hint, will the ice cube affect the temperature of the lake? And the answer is no, it won't. It won't, just because it's inconsequential. But again, it will technically, it will cool the lake's temperature a little bit, but we're going to assume it's not cooling it at all. All right, so next phase, look at the melted ice water warming up. So this now can start to cruise along. The change in entropy for this cube during the phase where it's melted and it's warming up is once again defined as the amount of heat that goes into or leaves the object over the temperature at which that heat flows in. I mean, that's what entropy, that's how we're talking about entropy. This is the mechanical, the non-statistical way of looking at entropy. So if I'm looking at what I just wrote down as entropy, the change in entropy is given by the amount of heat that flows in or out of a material and the temperature at which it flows in or out. All right, so let's just keep going with this. Warming up means this. I can do this transfer function. It's going to be mc dt all over T. What was the mass of the cube? Now I'm going to write specific heat capacity of water. Okay, and just to reinforce, where did this come? How did I go from this to this? Just to rewrite it again, because Q equals MC delta T. And if I take the differential of that, if I differentiate both sides, then dQ equals MC dt. So once again, that's how I got this numerator right here. Let's process this. Number 16, the change in entropy for the melted ice water warming up to the lake's temperature is going to be the mass of that cube, hasn't changed still for me, it's 0.026 kilograms. The specific heat capacity of water, which we better look that up, natural log of T final all over T initial, and I better specify my boundary conditions. That's T initial, this is T final. So with numbers, the change in entropy for this melted ice cube's water warming up to the lake's temperature, 0.026 kilograms, times the specific heat capacity of water, that is given to us in this table right here on your screen from your textbook and in your notes. Well, this might, yeah, well, it is for water. It's in your notes. For water, 4187. And that there's always somewhat, sometimes you see it as 4186 or 4184, but I guess we'll use 4187. 4187 is the specific heat capacity for water as it warms up. So this will be 4187, drag along the units, joules per kilogram, Kelvin, natural log, final temperature. Well, the final temperature is the lake temperature. So I need to convert. So I'll do the conversion right here within this argument. This melted ice water reaches the lake's temperature, and the lake's temperature is 80 degrees Celsius. So when I convert that, I'm just going to add 273.15. And now I can call that the Kelvin. 80, because my lake is just sitting there at a temperature of 80 degrees. My denominator is the initial temperature. This ice started out at freezing, 273.15 Kelvin. So let's get a number on that and store it. .026 times 4187 times natural log, times natural log, lots of parentheses. All right, I get a number. Now I'm going to double check it. Store memory C, store alpha C, and let's redo it. 0.026 times 4187 times the natural log of 80 plus 273.15 divided by 273.15. Okay, I'm getting the same number twice, so I guess that's good news. Here is our answer. So let's look at the ice water warming up to the lake's temperature. Done. Done. So we now have tracked all of this entropy. And I would expect the entropy for the ice to increase. If heat is flowing into the ice, anytime heat flows into an object, it always increases its entropy. I mean, that is just a simple statement that might help. If heat flows into something, that something's entropy has to increase. It can't stay the same. It can't decrease. Okay, so I'm going to do this. Delta S for the cube is basically going to get, is basically what I have there in memory location A. Memory location A is storing the result for the warming ice, the warming solid, plus memory location B. Memory location B was the change in entropy for the melting ice, plus memory location C, which is the change in entropy for the melted ice water warming up to the lake's temperature. And if I add that all together, alpha A plus alpha B plus alpha C equals 82 and some change. 82.41 joules per Kelvin. I'm going to put that in memory location D, store alpha D. Okay, and double check that. Alpha A, alpha B, alpha C. Okay. I'm not seeing any mistakes yet, so I'll go with that. That's the total change in entropy for the ice cube, step 20. Okay. Let's look at the change in entropy for the lake. Okay. Look at lake's change in entropy. And you might say, well, the lake didn't change temperature because it's so vast compared to the ice cube. And that's true. We can safely say the lake's temperature didn't really change. However, there's still heat flowing into the lake. So, and that's a real key takeaway. If heat flows into something, it's going to increase that something's entropy. And I need to correct myself. Actually, heat is leaving the lake. So I'm going to write that. I'm going to write it like this in step 21. Heat is leaving the lake. And it's leaving the lake. Heat is leaving the lake at a constant temperature. So yes, temperature is constant, but if heat is leaving the lake, the lake's entropy has to be decreasing. All right, so let's track that. All right, so 22, we have to go back for the ice warming up. For ice warming up, we got to go back to these stages. Now, but now we're looking at it from the lake's perspective. From the lake's perspective, this is the change in entropy for the lake, L for lake. It's defined as the heat flowing in or out all over the temperature. Okay, and I can write it for the lake. I can do it like this. Temperature is a constant because once again, the lake's temperature doesn't really change. So I'll write it like this. I'm left with this expression, and then the question is, what is the integral of dq? And the answer is q. So we can do this. The change in the lake's entropy during this phase is going to be Q over T equals MC delta T all over T. Hang on. No, I can, that is correct. It equals MC delta T all over T. And this is T out. I better use subscripts here. That's what I was kind of fumbling over. All right. T subscript L is the temperature of the lake. The temperature of the lake for the third or fourth time, this is constant. It's just going to be sitting there at 80 degrees Celsius. However, this delta T right here, this is the change in temperature for the warming ice cube. Because again, we're considering what's going on as far as the ice cube warming up. The ice cube is just warming up. It's not melting. It's just warming up. So this is what we're looking at in step 25. The change in entropy for the lake is going to equal the mass of the ice cube, which is 0.026 kilograms. The specific heat capacity of the ice, 2220 joules per kilogram Kelvin, times the change in entropy for the ice. The ice ended up at 0 degrees Kelvin. So I'm going to write that as 273.15. That was the final temperature, because remember, delta T still equals final minus initial. All right, the final temperature was 273.15. The initial temperature was, for me, negative 89. So I'll just do the conversion right here. So you can see it's pretty meticulous. Negative 89 plus 273.15. That's my delta T. Right. And that is good, except before that. 273.15 is my final temperature minus the initial temperature. And this whole argument is going to have units of Kelvin or Celsius degrees. And remember, 1 Celsius degree is the same as 1 Kelvin, but 1 degree Celsius does not equal 1 Kelvin. So just throwing that out here. And then I have to divide all of this by the temperature of the lake. And the temperature of the lake is just 80 degrees plus 273.15. That's it, Kelvin. Okay, so this is so complicated. I'm going to just be careful here. This is, all right, so this is M, MC delta T, that's M. This is C, and it's C for the warming ice, 2220 joules per kilogram Kelvin. This right here, this delta T means this must be final temperature. And all of this here, this must be the initial temperature. And this is the lake's temperature, which is just sitting there at a constant value. Okay, so let's do that. 0.026 times 2220 times 273. I should make a note. I got a number of 14 and some change. But I actually need to note that this is a negative. This is a decrease in entropy, joules per Kelvin. But the answer for me is negative 14.546 joules per Kelvin. I need to store this in calculator memory location E. And let me just talk about that. This, technically speaking, maybe I should have added this. I should have prepended a negative sign here. This should have been a negative. This should have been a negative here, you could argue, and this should be a negative. And I'll just make the note here. Note, Q is leaving the lake. So that's why I'm going to note that, yeah, Q is going into the ice, but Q is leaving the lake. How much heat is leaving the lake? And the answer is it's the same amount as the amount of heat entering the ice from the lake. And that's why, again, I'm prepending that negative sign, because that's how we keep track of, this is how we specify a loss of heat. Okay. Okay, so I'm going to just double check that. Store alpha E 0.026 times 2220 times 273.15 minus negative 89 plus 273.15 divided by 80 plus 273.15 minus alpha E. Okay. Getting the same answer twice, so that's a good sign. Okay. Onward. Now, what's going on with the lake's entropy while the ice melts? While ice melts, it's warmed up to its melting temperature, Q continues to leave the lake. So that's going to be if heat is leaving the lake, I know one thing: the lake's temperature doesn't change, but the lake's entropy will go down, because, saying it a third time, heat is leaving the lake. So this is it. The change in entropy for the lake during this process, the process where the ice is now melting, taking heat away from the lake, I can start off here. I always kind of just start off at the basic statement. T is constant. So I'm going to bring T, and this is T of the lake. The lake is not changing temperature. So then the integral of dq here, this will just be, once again, m of the water times the latent heat of fusion for the water. So this thing, and this is confusing, don't get me wrong. This is lots of meticulous steps here. This is, I'll just say the integral of dq equals q, and for melting ice, q equals ml. This is chapter 18. So with numbers now, 28. Change in the entropy for the lake during this process is going to be 1 over the lake's temperature, which is still sitting there at 80 degrees Celsius plus 273.15 times mass of the water, which is 0.026 kilograms, times latent heat of fusion, because the water is now changing from solid to liquid. That's a fusion phase change. And that was 333 times 10 to the third joules per kilogram. So, and I forgot my units here. This is K for Kelvin. All right, 29. The change in the lake's temperature for this process is going to be whatever the calculator says, 1 divided by 80. It's 0.026 times 333 E3 negative, because I'm going to do that prepending of a negative. So it's negative 24.5 0.516. And let me just make a big deal about how I really do need to indicate that I'm using a negative value here, negative. And this is negative because, let me say it again, the heat that's entering the ice cube is exactly the same as the heat leaving the lake. And the negative is taking care of the fact that heat's leaving the lake. Okay, so let me double check that and put this in calculator memory location F. Joules per Kelvin, calculator memory location F. Store alpha F. And then let's do a quick redo. All right, I did it twice and I get the same answer. Last step, and then we add everything together. One more phase. Now we have the melted ice water warming up. 29, 30. While melted ice water, while the melted ice water warms up, heat continues to leave the lake. So again, I know during this phase, the lake's entropy will decrease because heat's leaving it. Less entropy means less chaos, less randomness, less violence going on with the molecules. While melted ice water warms up, Q continues to leave lake. Okay, so let's track that. The change in entropy for the lake during this process, just starting at the definition, just because it's comfortable. All right. Once again, this is T of the lake. That it is a constant. So that's coming out of the integral. So the question is, what is the integral of dq? And the answer, the integral of dq is simply MC delta is simply Q. The integral of dq is Q. So Q over T. This is the T of the lake. This is the temperature of the lake. And this is the heat. So maybe I'm going to do this right now. What I'm just doing here, this is the heat leaving the lake, entering the warming water. So step 32, number 32 says change in the lake's entropy for this process is 1 over the lake's temperature, which is 80 degrees Celsius, converted to Kelvin. I'm just plugging numbers into 31 times, and now here's my negative sign. Q is MC delta T, mass of the cube, specific heat capacity of the cube. Well, maybe I better put water times delta T for the water. I'll do it like that and do another step with numbers, with more numbers. Negative 1 over 80 plus 273.15 Kelvin. Kelvin should have been here. Times the mass of the water, 0.026 kilograms. Times the specific heat capacity of water. We looked that up before. We used 4187 joules per kilogram Kelvin, times the change in the water's temperature. The water started off, well, it's final minus initial. The water ended up at the lake's temperature, 80 plus 273, this is cumbersome, 273.15 That's the melted ice water's final temperature. That's the lake temperature. It started off at its melting point. It started off as freshly melted ice water, 273.15. And that's it, but I'm going to double check everything here. I'm going to notate some stuff just to make sure. Okay, this negative sign makes sense because heat is leaving the lake, so I got to have that negative sign. This is the lake's temperature converted from Celsius to Kelvin. Okay, this is the this whole thing here again. This is the amount of heat leaving the lake. So this is Q leaving lake equals Q entering melted ice water. So that looks okay. And Q entering the ice water, that's not a phase change. It's just a warming process. So it should be MC delta T. MC delta T is final. My melted ice water ended up at that temperature. It started off at that temperature. So far so good, unless you guys see something that I'm just missing. Let's get a number on this. Okay. 24 and some change. I'm going to redo this. But before I redo it, I'm going to stick it in calculator memory location E, F, G, G. Yeah. Okay. So let's do a redo. I'm getting the same number twice. All right. Good heavens, this is quite the problem. But good. Good. This is a lot of chapter 18 and chapter 20 stuff. So it's good to have, you know, a mixture of past topics. So that's it. So the total change in the lake, I'll write it like this, total change in the lake's temperature is going to be whatever I got in memory location E, yeah, E, which is some negative number, plus whatever I got in memory location F, which is another negative number, plus whatever I got in memory location G. And I just want to double check myself. This was for warming ice. Warming ice, that's the change in entropy during the warming ice phase. And I'm just looking back on step 25. Okay, that looks good. This is the phase change. This is the heat leaving the lake to break the bonds of the ice's molecular bonds, the covalent bonds between the hydrogen and oxygen. This is phase change. And then, so that looks good for EF. EF, okay, that looks good. And then G was, again, the warming melted ice water. melted warming ice cube. Okay, so if I do all of that together, 36 alpha E plus alpha F plus alpha G, negative 63 and some change. Joules per Kelvin, EFGH. I'm going to put this in memory location H. So 37 says, wow. The total change in the entropy is going to equal the total change in the entropy for the ice cube that was warming up, melting, and then warmed up again, plus the change in the lake's entropy, which is going to be given by memory location D plus memory location H. Okay, I'm almost scared to do this. Store alpha H. All right, plus alpha D. 18 and some change, 18.69. Total change in the entropy is 18 positive, 18.693 joules per Kelvin. So what's my answer? My answer is 18. My answer is pretty much the same again. If there's a smidge of difference, it's because of, again, I'm using 273.15, and I believe Wiley Plus might use just 273, but I'm well within 2%. So a big takeaway here is, aha, entropy isn't conserved. When we first had this conversation, you might think, well, whatever entropy gained by the ice is going to be offset by the entropy lost by the lake. It's not like that. Aha, entropy is never conserved in real life. Theoretically, you can have theoretical situations where entropy is conserved. And that's what that reversible process is referring to. But in real life, if you do anything, if anything happens, a molecule moves from point A to point B, you sneeze, a star explodes, ice cube melts. If anything happens, this is the arrow of time sort of point. If anything happens, entropy increases. So I can say 41, change in entropy always increases. That's a big, big deal. That's the arrow of time, always increases, again, in real life. All right, so what time is it? Good heavens, this has been time consuming. It is now 9:07. Let me take a 5-minute break. I got to run, go do something. I will see you guys. We will reconvene at, I'll say 9:13 a.m. See you at 9:13 a.m. 5 or 6 minute break. Okay. And I'll leave all of this on the screen. I might need one more zoom out. Getting kind of hard to read though. I understand that. But I will see you at 9:13. All right, we're back. Sorry I'm late. I had to take care of a minor emergency. But let's see, before we move on, I actually think this might be the most time we spend on a problem. Although I don't know. You guys could do this a lot faster, especially with practice. But for right now, I guess this is still quite a bit of time. I want to see how people are doing on the old leaderboard. This is chapter 20, quiz 1. Let me just get a glance. Right now, before I even take a look, I'm just hoping somebody's got this answer correct because it's so many bits and pieces. All right, so this is chapter 20. It's probably gone. All right. 1 second. CH20 quiz 1. Physics 212. Okay, well, that looks good. Okay. All right, good. Yeah, most people got it right. So not everyone. And again, for those of you, couple people, same thing. You guys ask for help. And if you need more time, I'll give you more time, but we'll determine how much more time you need at the end of class based on how everything else goes. So I'm going to go in and make our second quiz available, which will not take this much time. But it's like cough medicine. Might not taste good, but it's good for you. Although I've always liked the taste of cough medicine. Robitussin DM, I don't care what people say, that tastes good. Chapter 20, quiz 2. Chapter 20, quiz 2. It's now available until 11:30 a.m. And I can make one more tweak. Okay, you should see it. Chapter 20, quiz 2 is now available. And I guess I better get rid of my scribble. This is, so let me just keep repeating this. What we're about to solve is a quiz. We're about to solve chapter 20, quiz 2, which is also a homework problem. So once again, do your best to not only get this quiz question correct, but then just jump right into the homework today or tomorrow and finish the homework version of this. Again, while it's fresh, because I think that will be more reinforcing if you just, bang, bang, you hit it today and then hit it again tomorrow, or that's the goal. All right, so let's see here. This is a PV diagram. PV diagram, we have 2.47 moles of an ideal monoatomic gas. So this is a key word. Ideal means you get to use the ideal gas law. Monoatomic means F equals 3. F equals 3 means there are 3 degrees of freedom, one for translational kinetic energy in the X dimension, and then a second one for translational kinetic energy in the Y dimension, and a third one for translational kinetic energy in the Z direction. There's no rotation going on. It's just a single monoatomic ideal gas, like helium. Just think of helium, for example. And it's taken through this cycle. And we know a lot about the cycle. So that's it. We know N. We know the number of moles. N is 2.47. F equals 3. Ideal gas law means PV equals nRT. And then we know a bunch of stuff. The first question is, what is work divided by P naught V naught? So let me, before we get into the nitty gritty, just remember, what is work? I'm going to indicate positive work. The amount of work going from A to B is indicated by this purple area. So I am showing you this shaded area. This is positive work. That's positive work. How do I know it's positive? Because I'm going from a lower volume to a greater volume. The piston is rising or the balloon is getting bigger because gas pressure always exerts an outward oriented force. And in this case, not only is the force from the gas pressure oriented outward, but the actual movement is outward as well. And that's positive work. But I'm going to crosshatch this in orange. What you're seeing here, all of this is negative work because I'm going from a higher volume to a lower volume. Okay, so this orange is negative work. So what I'm going to highlight here in red, red, this is net work. The amount of work indicated in this red crosshatch region, that's the net work done. Okay, so just wanted to throw that out there because I have negative work and positive work, and my net going from A to B to C, I'm doing negative work overall. All right, so let me erase all of that. I just wanted to reinforce. I just wanted to make those points for reinforcement purposes. Okay, but the question here says, for 2.47 moles of monoatomic ideal gas taken through the entire cycle from A, what is this result as the gas goes from A to C along path ABC? So from A to B to C, that's the path we're looking at. From A to B to C, what's work divided by P naught V naught? And I know this is isochoric. So for this isochoric process, I have some of my answer. Isochoric means work equals 0 because the volume doesn't change. If the volume doesn't change, there can be no work that happens, even though the force resulting from the gas pressure is not equal to 0, but the work is 0 because nothing moves. This is isobaric. Isobaric. And in this case, work is going to be greater than 0 because I'm going from a lower volume to a higher volume. So let's get this answer. Number one, for steps A to B to C, well, I'll do it like this. All right. The work from A to B to C equals the work from A to B plus the work from B to C, as indicated in that visual. The work from B to C is 0. So I just need to find out the work from A to B. The work from A to B is equal to the integral of P dV. This expression right here, this is the most general process, the most general purpose expression for work, integral of P dV. So no matter what, I mean, you could be completely stumped about everything, but you know one thing, work is the integral of P dV. Okay, so that's just going back to ground zero and getting your head screwed on straight, because that's always true, no matter what anything else is telling you. So for an isobaric process, I can bring pressure out of the integrand because isobaric means constant pressure, and this is constant pressure. Look, that's a straight line. Constant pressure means isobaric. And then I better have some initial volume to some final volume. So that's going to equal P. What's the integral of dV? The answer is V. And then if I evaluate it from some initial volume to some final volume, that's how I get P delta V. And I guess I better keep going over here. Okay, so the work from A to B is going to equal that pressure. This pressure is P times delta V. Pressure is P naught. Delta V means V final minus V initial. My final volume is V1. My initial volume was V naught. Okay. My final, so again, I'm looking at state A. I'm looking at going from state A to state B. So my pressure is constant at P naught. I end up at my final volume is V1. My initial volume is V naught. But the problem is telling me that V1 equals 5 V naught. So this is where you keep going back to the question, reading the question a bunch of times to pick off all of the details. So V1 is 5 V naught minus V naught. And so the work from A to B, if I pull out common factors, is P naught V naught times 4. But I'm not after that. I ultimately, for the first part, I'm after the work from A to B over P naught V naught. That's how I'm getting 4, because I have P naught V naught times 4 all over P naught V naught and just 4 with no units. So clever, but it definitely gives us a chance. This is a good problem to really reinforce basics, the basics of chapter 18, 19, and 20. Chapter 20 tends to throw problems at you that really do kind of recycle chapter 18 and chapter 19 issues as well. That's the answer to A. Now we have to talk about B. Part B is saying, what's a change in internal energy? Part B is saying, what is the change in internal energy divided by P naught V naught for this system going from B to C? All right, so we're starting at energy state B and going to energy state C. So right there, for that process, going from B to C, we need to find the change in internal energy and then divided by P naught V naught. This is, again, this is isochoric. That's an isochoric process. So that does trigger one thought process. I remember, and I've tried to make a super big deal about this. I'm going to do number 6 here, 5, 6. Change in internal energy can be calculated in many different ways. Some will make more sense than the others, but no matter what, it's always NCV delta T. This is always true. And then that's my numerator. This is my denominator. So again, I've really tried to stand on my head and just keep saying over and over again that change in internal energy equals NCV delta T, even if it's not a constant volume process. In this case, it is a constant volume process, so it works out, but it didn't need to be a constant volume process. Number 7. All right. And I better do it like this. P naught V naught. Let's keep hammering on this. So the change in internal energy all over P naught V naught, going from thermostate B to thermostate C, is N. I'm just going to leave that as N. CV is F over 2R, because CV is always F over 2R. Delta T is final temperature. So this is going to be the temperature at state C minus the temperature at state B. And all of this is going to be over P naught V naught. And so let me just sanity check this. This is N. All right, so N, CV, and yeah, I do know F is 3 because it's a monoatomic ideal gas. And this is final minus initial. Okay, I'm good. I think I'm good with step 7. Step 8, just keep hammering away. Change in internal energy over P naught V naught equals, F is 3. So here's how I'm going to do. I'm going to say F over 2 is 3/2. And then I'm going to multiply through. I'm going to do this for a reason. NRTC minus NRTB. And why am I doing this? Because I've kind of looked ahead a little bit. I don't know temperature values all over P naught V naught. So I'm thinking to myself, I don't know my temperature at C, and I don't know my temperature at B. But I am thinking of the Swiss Army knife of thermodynamics, because here I can say ideal gas law. I can say PCVC equals nRTC, and I can do the same thing here. PBVB equals nRTB. So I'm going to do that substitution because that way I can keep making progress even though I don't know the temperature. So I end up with 3/2 times 3/2 times PCVC minus PBVB all over that P naught V naught. Let's keep working. All right, number 10. So all of that equals 3/2 times PC. Well, now here's something. We know that, oh, that's fine. All right, so equals PC. PC is given to us from the graph. PC is given to us as 2 P naught. So if I look at the graph, the PV diagram, my pressure at state C is 2 V naught. So 2 P naught. This is my pressure at C times VC. My volume at C, according to my graph, is V1. Got it. Minus PB. My pressure at state B, according to my graph, is P naught. Times my volume at state B is also V1. All of that over P naught V naught. Let's keep going here. So the question is, I have 3/2 and 2 P naught V1 minus P naught V1 is just simply P naught V1 all over P naught V naught. So I have 3/2 times, you can see the P naught, I can cancel the P naughts here. And I made a typo. Let me fix this little typo. This should not be V1, it should be V naught. All right, so that at the end of the day, I get 3/2 times V1. V1 is 5 V naught all over V naught equals 7.5. Good heavens. Quite the journey. That's the answer to part B. I do know, and I would expect internal energy to increase. So the fact that this is a positive does make sense. I'm going from a lower isotherm. Remember that conversation. I'm going from this isotherm at energy state B up to this isotherm at energy state C. So that's why you know the internal energy is going to increase. I'm going from a low temperature to a higher temperature, just based on that isotherm overlay. That's it for part B. What's the change in internal energy for one cycle? And so we are going to finish that right now. This is for part B. This was for part A. So let me just, this was part A. This was part B. Part C says, what's the change in internal energy for a cycle? And you know that because internal energy is a state variable. It's a state variable. It does not care about path or history. It only cares about its current and final state. So because internal energy is a state variable, change in internal energy equals 0 for a closed loop. So we're done with part C. That's part C. Okay. Part D says, what's the change in internal energy from B? No, yes. from B to C. No, let me see. What is change in entropy? I was just going to say we just did that. All right, so let me erase this a little bit. Part D says, what is the change in entropy? What is the change in entropy as we go from state B to C? Okay, so that looks, here's state B, here's state C. So right now we need to find the change in I keep saying that. We need to find the change in entropy from state B to state C. That's our task right now. I'm just going to write over here just because my screen is getting full. So I'll just keep writing step 15. I left off at 14. Step 15, change in internal energy is defined as integral of dq over t. Okay. From state B to, so this is isochoric. For an isochoric process, for an isochoric process, I can use a transfer function. I can say the change in internal energy is going to be integral of n CV dt all over t, and I better talk about that. I basically, and this comes exactly, this is exactly like the last problem. Just a little sidebar here. Little sidebar. The integral of dq over t, this is my transfer process. I'm saying that's going to be equaling the integral of n CV dt over t, because once again, Q, the specific heat capacity, molar specific heat capacity is M NCV delta T. This right here, this is the molar specific heat capacity for a process at constant volume, and we are dealing with a constant volume process. So the difference between NCV delta T and NCV dt is just, I just took this is the differential form. This form right here, NCV dt, is the differential form of NCV delta T. Okay, so I said that before, probably multiple times, but it's good to repeat. So we have the integral of, well, I can pull out my constants. N comes out because it's a constant. CV comes out because it's a constant. And I know the natural log of, I know that the integral of dt over t is the natural log of some final temperature over some initial temperature. Okay, and then I'm evaluating this from some initial temperature to some final temperature. All right, so now we're back in that situation. I don't know the temperature. So not to worry, ideal gas law to the rescue. And I am kind of running out of room. So I'm going to keep going, step 16 to step 17 to step 18. NCV, which is going to be 3/2 R. I can make that substitution now. Because CV is F over 2R. Natural log. All right. My final temperature, let me do it like this. My final temperature is whatever my temperature is at thermodynamic state C. My initial temperature is whatever it was at initial state B. All right, so I'm going to do ideal gas law, and I am kind of running out of room, but I'll squeeze it in. All right, here's TC. Ready? PC VC all over NR. That is my temperature at C, N times R. Here's my temperature at B. Ready? PB VB all over NR. So let me make this look more coherent. All right, what I have here, that's TC for aforementioned reasons. I'll just, again, blurt that out. Ideal gas law says PCVC equals nRTC. So this is TC, and all I'm doing, I'm saying TC therefore equals PCVC over nR. Okay, same explanation here. This denominator represents the temperature at B for the same exact reasons. So that's my argument. That's my argument's numerator and denominator for that natural log function. And now I guess I have to make room. Okay, I'm going to go down here for step 19. 19, ready. The change in entropy from B to C is therefore, my next step is 3/2 times nR natural log, and look at the argument to my log function. What do I get nR cancels, and I'm going to end up with PC VC all over PB VB. That's what I end up with. So that simplified quite nicely. But I can also say the following. VB equals VC. So this cancels because of isochoric. VB equals VC. Why? Because from the graph and because it's an isochoric process. You can see the graph is showing this as an isochoric process. So all of a sudden, much easier, much more digestible. Step 20 is, let's keep running with it. 3/2 times n. I know the value of n. I know the value of r. I just need to take the natural log of PC. PC, according to my graph, is 2V0, 2P0, sorry. PB, according to my graph, is P0. So this should equal 3/2 times n. For me, n is 2.47 moles times r. R is 8.31 joules per mole Kelvin. Natural log 2. From a dimensional analysis point of view, moles cancels with moles. I end up with joules per Kelvin. So that's good news. Joules per Kelvin are the units. So dimensional analysis looks good. Just got to get a number. 3/2 times 2.47 times 8.31 times natural log of 2 is 21 and some change. And we're done with this part. 21.34 joules per Kelvin. This is the answer to part D. Great success. Part E, we're done with. We can start and stop part E, because what's the change in entropy for one full cycle? This is where you remember that entropy is a state variable. So for part 2021, change in entropy from A to B to C back to A equals 0 joules per Kelvin, because entropy is a state variable. Because entropy is a state variable. And that's the answer to part E. Okay. Pretty heavy. These two problems are heavy. All right, so you guys can Keep working if you need another moment, or if you're completely done, please stand by while I get quiz 3 available. Quiz 3. Okay, I think chapter 20, quiz 3 is now available. Lots going on here. Huh. Okay. Entropy. I mean, this chapter is about entropy and heat engines. So entropy tends to be thought of as a very sort of exotic or abstract concept, and heat engines tends to be thought of as a very practical, lawnmower engines, automobile engines. And you can see and remember that BBC order and disorder production really does, I think, do a good job. It will once we get through all of it, really linking entropy and efficiency and a bunch of stuff, the arrow of time. All right, so this is not a PV diagram. That's the first thing I'm noticing. This is not a PV diagram. It's a temperature versus entropy diagram. All right, so that, again, is the first thing I'm noticing. I have temperature on my dependent axis, and my independent axis is entropy. All right, a 2.74 mole. So I know N equals 2.74. It's ideal, which means I can use the ideal gas law. It's monoatomic, which means F equals 3. 1 for X, 1 for Y, 1 for Z in terms of just translational kinetic energy. There's no rotational kinetic energy. It undergoes a reversible process. Fine, so that's a keyword. Reversible basically means you can run the process forward and the process can run backward with no loss of energy. There's no friction losses. There's no non-conservative work. You can kind of naturally go from state A to state B and then from state B to state A with everything being exactly as it was in terms of the state variables. All right. It's scaled. I have some value for TS and S subscript S. Fine. How much energy is absorbed by heat? All right, so let's begin this conversation. How much energy is absorbed by heat? So number one, I'm going from TS. So from TS to, well, I'm going to do it like this. I'm going to call this state A and state B. From A to B, QAB equals the $sign. Okay. Just double checking. How much energy is absorbed as heat by the gas? All right, so number two. Well, what's relating? I have a graph of temperature and entropy. So maybe I'll just fall back and say, well, I'm going to go back to the basics. Change in entropy does equal the integral of dq reversible, and that's where this term comes into play, all over t. So I am seeing a linkage between entropy and heat. So I might hammer on number 2. I might keep focus on statement 2. What if I take the derivative of both sides? If I just take what if I differentiate that entire line? I'm going to differentiate the left side and differentiate the right side. If I do that, because I want to get to Q, number 3, then if I differentiate, I basically have ds is my left side. The derivative of an integral is just the argument. So that's like saying, what is the derivative of the integral of dx? And the answer is just dx. So same thought process here. My right side is just going to be dq all over t. So I'm liking that because if I multiply both sides by t, I'm going to multiply the right side by t, which means I have to multiply the left side by t. Finally, I can get to an expression for dq, which is, after all, that's what you're being asked to figure out. How much heat got absorbed during this process from A to B. So I'm going to say dq equals t times ds. And this should look familiar to you. Well, it should look familiar to you soon. Once again, I'm after dq. So I'm going to take the integral of both sides. And if I want it to be, I'd say, well, this is from some initial q to some final q. And this is from some initial entropy to some final entropy. And I'm going to just say my initial temperature, my initial heat flow is 0. So I'm starting off with no heat flow because I'm just looking for the change. Starting off with no heat flow, and I'm ending up with some final heat flow. So number 5 then can be written as the integral of dq is just, I'll do it like this, q from q equals 0 to q final equals q, equals area under graph. Area under t versus s graph. That's a big deal. And for those of you who worry about such naming conventions, this is the fundamental theorem of calculus, part B. But you guys know this, from a long time ago, if you have a graph of y versus x and you have some function like that, and if you needed to find out this integral from some initial x to some final x, you know this from your previous learning that it's this area. This area is, in fact, the integral of y dx with the boundary conditions. So you've done this before. It's called the fundamental theorem of calculus, part B. So that's what I'm going to tap into. That's what I'm using here. Number 6 says if I evaluate my left side, I'm just going to get, and this should be q final equals q. All right. So a little typo there. So I'm going to get q equals the area under the graph. This is a trapezoid. And the area of a trapezoid, and you could say, well, it's the area of a trapezoid, or you could say it's the area of a rectangle and a triangle. But the area of a trapezoid is 1/2 h1 plus h2 times the base. You don't have to memorize this. It's literally going to be given to you on the exam. And if it wasn't, you could ask me. You're not expected to memorize this, although you could argue maybe you should be. But all right, here's h1, because now I'm just in geometry mode. I'm just figuring out the area of a trapezoid. That's h1. which is called TS. Here's H2. That looks like TS over 2. Here's my base. All right. So if I do that 1/2, if I do this, this area is given by 1/2 H1 plus H2 times base. So I'm just going to write down 1/2 times H1. This is H1. The answer is TS. Plus H2. This is H2, height 2. That's TS over 2. Base is this. Base is going to be, let me look at the base since that's complicated. There's my base. So for this base, little sidebar note, I have 3 boxes. This is my boxes. So I'll write it like this. My base is 3 boxes. But I need to convert. I'm going to convert. Here's the conversion of 3 boxes. 3 boxes is basically the same as S over 4 boxes. So that's my conversion factor, because you can see from the graph that you can see that S subscript S is equivalent to 1, 2, 3, 4 boxes. So that's how I do it. You can do it a different way. But boxes canceled with boxes, so I am left with the amount of heat that flowed into the system is 1/2 times TS, 1/2 times 3/2, because 1 plus 1/2 is 3/2 TS times 3 over 4 times S subscript S. So with numbers, I have 3/4 times 3/4 times TS times S sub S. TS is given as 425 Kelvin. S subscript S is given as 21.1 joules per Kelvin. All right, so ending up with joules, that's good. So let's see if this is the right answer, just because there could be a mistake. Okay. I get, my calculator says 5,044 and some change joules, and they want the answer in terms of kilojoules, so 5.04 kilojoules does make sense, and that's the answer to part A. That's the amount of heat that enters the system, and this was based on a temperature versus entropy graph, so different. Part B says, what's the change in internal energy? Okay, I don't know. Let's do, all right. So I need to find out the change in internal energy from state A to state B. And here's going to be my first thinking. You can find lots of ways to calculate internal energy, but this is my comfort food. It's always going to be NCV delta T, even if it's not an isochoric process. Because again, if you're looking at this, you're saying, well, Chris, this is the molar specific heat capacity for a gas undergoing an isothermal expansion. And that's true, but it's this whole expression here is applicable no matter what kind of process. So make sure you can explain. Make sure you could answer the question, why is that true? I mean, I've explained it many times, but That is always true. So I'm going to go with that because I do know N. N is 2.74 moles. I do know CV because this is a monatomic gas. CV is going to be 3/2 R. And I do know delta T. Delta T, my final temperature, so I'll just do, again, final minus initial. That's delta T. So even more specific, what is 2.74 moles times 3/2 times R is 8.31 joules per mole Kelvin. T final is TS over 2. T initial, T final, T initial is TS. Okay, so I guess that's good. Let's get, we know what TS is. We know that 1/2 minus 1 is negative 1/2. So 2.74 times 1.5 times 8.31 times TS times negative 0.5. Okay. So, my internal energy decreases. Negative 7257.74 dimensional analysis. Let's see, moles cancels with moles. This temperature difference is going to be in terms of Kelvin. So that Kelvin cancels with that Kelvin. And I do end up with joules. Dimensional analysis is good to go. And this can be expressed as negative 7.3, or I guess they're using 7.26 kilojoules. That's the answer to part B. Done with part B. Part C will be very, very brief. 8, 9, 10. How much work is done? What is the work done by the gas from energy state A to energy state B? This is a job for the first law of thermodynamics, which says change in internal energy equals Q minus W. And this is your dollar sign. So go ahead and solve for W. That's your dollar sign. You just figured out the change in internal energy, and you already figured out the amount of heat flowing into the system in part A. So you know that green variable, and then solve for that blue variable. And then we're done. So finish up that while I start to preheat quiz 4. Quiz 4 is now available. Let me just take a peek at the grade book. Okay, quiz 3, quite a few people are not done with quiz 3. So you know what I'm going to do? Since some people still need some work for quiz 3. One student needs some more time for quiz 2, so you'll get it. No worries there. Let's just do a 6-minute break. I will see you at 10:13. See you at 10:13 a.m. That way we can get more people catching up. Right. Let me reduce this. Okay, that's everything. 10:13. Chapter 20, quiz 4. I'm actually going to leave this up on the screen. I'm going to try I just want to try this approach instead of doing it from scratch, just talking through some existing content here. All right, and just highlighting things. Here's chapter 20, quiz 4. So again, you're going to get this quiz question correct, and then sometime today or tomorrow, just go right into the chapter 20 homework and do the same problem, and then think on it. Think on it deeper when you do it a second time via homework. In the first stage of two-stage Carnot engine, so if the term Carnot engine sounds brand new to you, again, shaking my head in a slight disappointment because you should have digested the lecture video by now. Otherwise, this is the first time you're going to hear that term, which is not the end of the world, but it's not as good as it could be. First stage of a two-stage Carnot engine. So that's what I'm drawing right here. In general, this is how you draw a heat engine. So we're switching gears. We are definitely stepping into a different topic within chapter 20. Whenever you draw a heat, there's a heat engine. So we go from, just take a little inventory of what we've been doing. We've talked about specific heat capacity. We've talked about phase changes, delta phase changes. We've talked about the first law. We've talked about processes like isothermal, isobaric, isochoric. We talked about adiabatic and technically adiabatic free expansion. And we've talked about the ideal gas law and kinetic theory of matter. So anyway, this is a discrete topic. And maybe I'm leaving off a few things here, but I'm just making that list to say we're going to add to this list now with something called heat engines. Heat engines, and I should have said, definitely talked about entropy here. So whenever you want to draw a simple representation of a heat engine, it's always just a circle. It's a circle with 3 lines. 3 lines, 1, 2, 3. A circle with 3 lines, and this represents a heat engine. And the question is, what's a heat engine? And the answer is a heat engine is a device that does work for us by harnessing heat energy. So that's a very good state. That's a very good luxury to have. In the case of a heat engine, you have to feed a heat engine some heat. The heat engine will do some work for you, and it will spit out some waste heat. All right, so what you see here, so that's in general. So what are some heat engines? You could have an internal combustion engine like in your car. You could have a diesel engine, which is an external combustion engine, like in some cars and trucks. What other heat engine? You could have a heat engine working in reverse is called a refrigerator or fridge. A heat engine working in reverse is also known as an air conditioner. And then you have lakefront. If you go to Lake Michigan, near large bodies of water, you have a lot of dynamic heat flow and temperature changes. And that behaves like a heat engine. It causes weather systems. It energizes. It can be energizing, or it can diminish energy. So there's lots of things that work as heat engines. There's something called a heat pump. You can go to Home Depot and buy something called a heat pump, which is basically like an air conditioner. So very far-reaching consequences of engines. We feed them a lot of energy. So if I go over here, we have a two-stage Carnot engine. I'm going to stick over here for a second. We feed engines energy in the form of hot heat. Hot heat is fed at a hot temperature. And why do we like heat engines? Because they do W work. And the second law of thermodynamics says no matter how perfect this engine might be, you're always going to get some amount of waste heat. And that's referred to as cold heat at a cold temperature. So don't be misled by these terms. You might say, well, what does hot heat mean? Isn't all heat hot? Basically, Q sub H versus Q sub C is referring to the temperatures that's coming in from a source of heat, and Q sub H is referring to the energy that leaks out or that dissipates at a lower temperature. And wherever you get the source of heat from, the temperature of that heat source or heat reservoir is referred to a hot heat reservoir, hot heat reservoir. And wherever this waste heat, this colder heat is expelled to, that's referred to as cold temperature or a cold reservoir. And again, if things are working out right, we're going to actually be able to convert the process of heat flowing, the process of this heat flowing from a high temperature to a low temperature, that's going to produce some work. So this is why engines are everywhere, because they do work for us. So then the question is, what's a source of hot heat? And the answer is burn coal. I mean, to use the dirtiest example possible, burn coal. What's the example of waste heat? This is just heat escaping to the atmosphere. And in the case of like electricity generation, what's the work? What's the work you can get? If you burn coal and that heat flows from a hot temperature to a cold temperature, this work might be manifested or exemplified as running a turbine, running a coal-fired steam turbine, running a turbine. So there's a lot, and let your imagination run wild. In the case of an automobile, instead of burning coal, you explode gas air. You shoot some gas, a mixture of gas and air into your piston. This is the whole piston example again. There's a cylinder, and inside your car you have cylinders, and then you have pistons that are inside of these cylinders like this. And how do you introduce heat here? You fill up this area right here with a mixture of gas and air. This is why you fill up your gas tank at a gas station, and your fuel injector basically fires or sprays gas air. It's like a spritzer, like a water spritzer. It spritzes that mixture of gas along with air into here, and then you explode it. What's a good way to explode that gas air mixture? One approach is a spark from a spark plug. So spark from a spark plug fires, and then you get boom. You get an explosion. That explosion generates heat. So this is your source of hot heat. Okay. So in the case of your car, the waste heat comes from your exhaust pipe. And just generally, in addition to coming out of your, in addition to escaping from your exhaust pipe, it just emanates from hot objects, like your engine manifold, your engine block. It emanates from hot objects. So, and again, the list goes on and on in terms of what's a good way to get heat. You could say, well, a good way to get heat is to do something that doesn't consume fossil fuel. That seems to be a good idea. So you need to find some heat that doesn't require the combustion of fossil fuels. And then you're off and running without any carbon footprint. But no matter what, you're going to get some work out of it. So this, but going back to our question now, heat energy is absorbed. All right, so right here, I'm feeding this energy some heat at some temperature. I'll call it, instead of T hot and T cold, I'm going to call it T1 and T2 just because I have multiple engines going on. So I am feeding engine S1. I am feeding engine S1 some heat, some hot heat at a hot temperature. And yes, this engine is doing some amount of work. And the second law of thermodynamics is that you're going to have to spit out some waste heat. So if I'm just looking at S1 right here. Let me zoom in a little bit since that's maybe hard to see. Okay. That's better. All right. So second law of thermodynamics says you're going to have some waste heat. And let me just indicate the heat that's getting wasted. You have to have some. Okay. So how much heat is being wasted? Q2 at a lower temperature. Okay. So that's engine one. Let's just step back for a second. Look at engine one. I am feeding engine one some input. I'm burning something and getting the heat from whatever it is I'm burning. It's doing some work. It's basically turning the wheels of a vehicle, for example, or a jet turbine in a jet airplane engine. And then I get some amount of waste. You always get waste. All right, so that's true in general. And specifically, in my case, they actually told me the numerical value for temperature one. So the temperature of my hot reservoir, this is my hot reservoir. The temperature of my hot reservoir is always T hot, or in this case, T1. It's always expressed in Kelvin. And I have a numerical value for that. All right, and then they say your engine S1 is doing its thing, but you're being clever, and this happens in practice. You're taking this waste heat and you're redirecting. You're basically reusing. You're reusing, and maybe even a better word is recycling. You're reusing or recycling this waste energy, and you're feeding it to another engine. A lot of, I thought I wrote it down somewhere, but a lot of times you have in older systems, you have a coal-fired power plant. And again, the problem with coal, lots of combustion products, very heavy carbon footprint. So if you have an existing coal-fired power plant, you're going to get some electricity out of it, and you're going to get a lot of waste heat. Now the thing is, let's take this waste heat and let's feed this waste heat to a new and improved natural gas fired generator. And natural gas has a significantly less carbon footprint compared to coal, which is why I don't think anyone's building coal-fired plants anymore, and they're decommissioning a lot of them. Although in other countries, in countries around the world, other countries I think are still building coal-fired plants. So that's a whole conversation. But that's what we're doing here. The energy is expelled at Q2 at a lower temperature, and I do know this lower temperature. So I have numerical values for my cold reservoir and my hot reservoir. The second state's absorbed. So that's why I have this visual here. Here's my second Carnot engine. And again, I'm being environmentally aware. So I'm going to take this waste heat. This is waste. And what is waste heat to engine one is now input heat to engine 2. So this waste heat now becomes input heat to engine 2, generator to engine 2, whatever you want to call it. The second stage absorbed energy is Q2 does work. So let's just go through and repeat. We like engines because you feed this engine some input heat from somewhere. In this case, it's recycled from engine 1 at some hotter temperature. This engine's also going to do work, and you're going to get another chunk of wasted heat at a lower temperature. And they gave me this value here as well. So I know all of these temperature values. That's the big picture. And this is good stuff. To me, I find this stuff interesting because I really like the whole idea of energy generation and clean energy and sustainability. I'm definitely into that. And this is what we're really focusing on here. All right, so the question is, what's the engine efficiency? All right, so let's start. Number 1, here's a great statement for efficiency. Efficiency is what you want over what you pay. Okay. That's efficient. That's always efficiency. What do you want? What do you pay? This Greek letter, this is Greek letter eta in step number 2. Greek letter eta. This is how you write it. It looks like a contorted N, but it's Greek letter eta. What do you want an engine to do? What do you want your lawnmower engine to do? I want my lawnmower engine to work. How are you going to pay for that? Heat. Okay. So that's always the case in terms of engines. We want engines to do work, and we got to pay for it. In the case of this setup, I actually have 2 work contributions. I have the work from stage 1, my stage 1 engine, and in addition to that, I'm getting some more work from stage 2 because I'm recycling the waste heat. How do I pay for that? I'm paying for that via my input heat, Q1. And you might say, hey, Chris, shouldn't that really be Q1 plus Q2? And the answer is no, because Q1 is my investment. This is my investment. My investment is Q1, which comes from burning something or recycling something or harnessing a natural heat source. This is my investment. Q2 is not my investment. Q2 is actually just some rejected heat that's getting repurposed. So that's why it's just Q1, not Q1 plus Q2. That's my efficiency. Let's keep going with that. Step number 4. Let's do the first law. First law means N equals out. Now, first law, I've been writing first law like this. Change in internal energy equals Q minus W, which is a fancy way, which is a way of just saying N equals out. N equals out. So it's basically saying whatever goes into the system will increase your internal energy. Whatever goes out of the system happens in the form of lost heat or work done by the system, or I should say on the system. Anyway, these are saying the same thing. This is the first law of thermodynamics. It's conservation of energy. So ultimately, first law of thermodynamics is conservation of energy. So good just to get a recap on that. Okay, so if N equals out, first law is N equals out, what's going in? The answer is Q1 is going in. So if I could actually do this, I probably actually should do this. If I just sort of drew an envelope, let me draw an envelope that looks like this. I'm just going to draw this brown box. And that brown box is basically my engine. You know, if you look inside this brown box, yeah, you see a 2-stage engine, but that brown box itself is my macroscopic aggregated engine. Okay, what's going into my engine in terms of the first law, because N equals out. Here's what's going in. Let me just highlight this one more time. This is what's going in. Let me zoom in. Okay, right here. This is what's going into the engine Q1. Okay, this is my input. That's not a good color. This is my input, right? Yeah, okay, here. I'm feeding my engine Q1. What's coming out of my engine? What's coming out of my engine? Work 1 and Q2. That's coming out of my engine. Similarly, for engine 2, what's going into my engine? Because N equals out. What for engine S2, what's going in is Q2 right here. What's coming out is work 2 and Q3, waste heat. So N equals out. That's all I'm doing. I'm just saying N equals out, and I'm keeping track of that because I need to find out how efficient this engine is. All right, so just to repeat, stage 1, this is going in, and this is coming out. So what I'm doing here in step 4, I'm just isolating work. So if Q1 equals W1 plus Q2, just algebraically rearranging that, work 1 is Q1 minus Q2. Why am I doing that? Because of this. Because of efficiency is what you want over what you pay. What do I want my engine to do? I want to do work. So I'm basically going to figure out what this numerator is. I need to figure out the total amount of work done by this engine. That's my numerator. So, and I'm pretty close because my second stage engine, what goes in is Q2. What comes out is W2 plus Q3. So here's the amount of work done by my second engine. Okay. So this is it. Here's my updated efficiency expression. What you see right here, this is the amount of work done in my first stage plus the amount of work done in my second stage all over what I invest. So for the umpteenth time, this numerator right here is what you want. This equals work. My denominator is what I pay. This is my investment. This is my payment. That explains number 5. Number 6 says, okay, number 6 comes directly from number 5 because you can see I have a negative Q2 plus a Q2. So number 6 is getting simple. So now we have to do a deep dive in number 7. Number 7 says the following. If and only if, IFF, if and only if you're dealing with a Carnot device, you can say the following. If you're dealing with a Carnot device, you get to use this ratio. This is a ratio. This is the Carnot heat temperature relationship. This was heavily derived. Learn this derivation. This derivation was presented to you in the lecture video and captured in your green sheets. And why do you learn, if you're going into science or engineering, why do you learn derivations? Because you need to have this insight. If you don't know the derivations, you're not going to be as deep a thinker as you otherwise would be. You're going to gain insights by learning these derivations. So this is just a big deal. This is such an important statement that I'm going to get very multicolored and say, you can use this expression, but it has to for sure be a Carnot device. It has to be a Carnot engine or a Carnot air conditioner or a Carnot refrigerator, etc. All right, so now that I've tried to stress that adequately, step 8. Step 8, all right, step 8 comes from this Carnot heat temperature relationship. So if I look at step 7, that's how I can get an expression for Q3. Why am I trying to get Q3? Well, I'm actually trying to get Q3 in terms of Q1. I guess that's the question I should have asked. Why am I doing this? why did I just do step 8? I did step 8 because I want to get everything expressed in terms of Q1 so I can get some cancellation, so I can take advantage of cancellation. So here's the bottom line. Step 9 comes directly from step 6. So here's step 6. Step 6 then feeds I go right from step 6 to step 9. Q1 minus Q3 over Q1. So here's Q1. Here's Q3, but Q3 again, here's my new and improved expression for Q3. Thanks to the Carnot heat temperature relationship, which is applicable only if you're working with a Carnot device, and my denominator is still Q1. So you can see the Q1s all cancel out, and then I get this aha moment. Aha. The greater, the aha moment is there's your answer because you know T3, you know T1, but the real takeaway here, in my humble opinion, is the greater the temperature difference, the greater the delta T, the more efficient. So in other words, if you can figure out how to make T1 super hot and T3 super cold, you're going to get a much more efficient engine. And that is actually a true statement, practically speaking, as well as theoretically speaking. The greater the temperature, that's why believe it or not, the engine in your car loves super cold days. The engine does. Everything else hates cold days, but your engine loves super cold days because the heat that you're feeding your engine by the gas exploding is really hot and outdoors is really cold. That is good. That is good. That's why we have high octane gas, because well, anyway, but everything else hates low temperatures because you get friction and viscous losses. But that's it. So the efficiency of this engine really is remarkably simply calculated because you know these temperatures. You know this temperature delta. This is T3 right here. Going back to this brown box, this is T1. So it boils down to, hey, make T1 as hot as possible, make T3 as cold as possible to get the greatest amount of efficiency. So that is our first thermodynamic engine efficiency calculation, which is a big deal. It is now, let me zoom out one more time. I kind of like doing it this way versus writing everything from scratch. All right. Let me get quiz 5 ready. Chapter 20, quiz 5. Okay. And it should be available now. Chapter 20, quiz 5. Okay. There it is. And again, let me interrupt. Let's get rid of all of this cowardly pre-written material. And that really is the right way to think about it. So Good to hear. All right. So we're going to do another heat engine problem. I made a super duper, not super, but super duper big deal about this LLNL energy usage spelling. All right, so I made a super big deal about what you see on the screen right now. And to me, this answers a lot of questions. Why do we study thermodynamics? Because of this screen. Why do I care about heat engine efficiency? Because of this screen. Why are there environmental considerations? Because of this screen. So really, this screen does answer a lot of why you would ever spend time studying chapters 18, 19, and 20. And this is really interesting. So this is 2020, pretty recently. Look how thick these lines are getting. Solar, that's actually becoming a pretty thick line. A few years ago, this was a pencil thin line. Nuclear is pretty big. And here's a question. Is nuclear energy, do you consider nuclear energy clean energy or green energy? Is nuclear energy renewable? Does nuclear energy have a toxic footprint? So anyway, hydro is getting thicker. Wind. Michigan is a huge state in terms of wind power. We actually generate a lot of wind power. We actually generate a lot of wind turbines. Geothermal, my dad had a geothermal pump. You basically put pipes deep into the ground. And during the winter, that deep ground location becomes a cold reservoir. So you basically just siphon heat from your hot living room to the colder ground. And in the winter, you draw heat from the cold ground to your living room to heat it up. Natural gas still very thick. Look at coal is getting super thin. I mean, we should probably step through what this diagram, what this is called this is basically just a flow chart, a ranking diagram. But this used to be super thick. That used to be a very thick black line. You can see that we still have thick lines for natural. Look how thick natural gas is. Natural gas is very popular. It's actually, relatively speaking, it's relatively clean compared to coal. So a lot of coal is getting replaced with natural gas. Petroleum, this is oil. This is literally digging oil out of the ground, pumping oil out of the ground, and just follow we pump oil out of the ground to produce gas for transportation and other petroleum products for industrial purposes. There's a lot of stuff. There's a lot of stuff made from petroleum-based products, polymers. A lot of carbon-based products exist in the world today. And then you can see, look at how much energy is getting wasted. Of this grand total of 92.9 quads, we're wasting almost 2/3 of it. And that's a problem. And you're going to have to waste some energy. Second law of thermodynamics says you're going to waste some energy, but you don't need to waste that much. And all you need to do is to study physics 212 and figure out how to make more efficient devices. It's that easy. All right, so let's go ahead and do our next quiz. Starting now. Okay. I forgot. let me just do this. Oh, there it is. Good. All right. This is homework problem 20.30. So make sure, finish this as a homework problem today or tomorrow. That's the goal. Okay, so just wanted to keep that there for record keeping purposes. All right. This is a Carnot engine. So I have a 513 watt Carnot engine. So I'm just going to do what I always do. Whenever I'm working with engines, it is a circle. That's my Carnot engine. Carnot engine is a circle. It's a circle with 3 lines. So I'm going to draw 2 vertical lines, one like this, one like this, one like this. And then because it's an engine, it's not an air conditioner. Hopefully we'll get to air conditioners today yet. But because it's an engine, I need to feed it heat. I hopefully will get some work out of it. And I have to reject some waste heat. And specifically, I'm going to feed it some hot heat at a hot temperature. And again, that might be in the form of you throw a log in the fireplace. You burn wood. That would be like the worst case scenario, a bad scenario, to get some work done. And second law of thermodynamics says you're always going to have some waste heat at a colder temperature. All right, so this is saying a 513 watt Carnot engine operates between a constant temperature reservoirs. So this is, everything here has to be Kelvin. So I'm just going to do, this is my hot temperature, 115 degrees Celsius plus 273. I think I will just use 273, not 273.15. That's my hot temperature. So that's the temperature at which I am somehow producing heat. Okay, that's good. My cold reservoir is sitting here at 44.1. So this equals my cold reservoir, my rejection reservoir. This is going to be 44.1 plus 273 Kelvin. That is my cold reservoir temperature, and that's given. What else? 500. So 513 watts. What is that representing? That's power. I know watt is a power. So let me just start making some commentary here. Number one. 513 watts equals power. All right. In this case, power is the rate of doing work. This is what we want engines to do. We want engines to do work for us. And this engine is rated for a power of 513 watts, which equals 513 joules per second. 500, a watt is a joule per second. So 513 watts is the same as 513 joules per second. So you know what I'm going to do here? That joule per second, I'm just going to say in 1 second. In 1 second, let's look at this engine over the time period of 1 second. In 1 second, I'm getting 513 joules of work out. 513 joules. And that's a big conversation because you see this number 513. And my thought process is, or my considerations are, well, it's 513, but does that equal QC, or is that my number for is that my number for QH or for QC or for work? And the answer is that is the number, that is the rating for work. That's just, and you sort of have to know that, or it sort of has to be clear. We have to recognize that it's 513 joules per second of work is what this engine is producing. That's how I'm doing it. So in 1 second, that's 513. Part A says, what is the rate at which energy is taken in as the energy as heat? So you know what this is? If I'm reading this, this is basically saying, what is Q sub H? Hot heat. Hot heat, Q sub H, is the amount of heat that's being fed to this engine or taken in by the engine as heat. So right now, this is the dollar sign. In 1 second, well, we'll find this out in 1 second. And then part B says exhausted by the engine as heat. So same deal here. what is exhausted heat referred to? And that is referred to as Q sub H. I'm sorry, Q sub C said that wrong. All right, so that's my dollar sign here. Okay, so now what? I don't know, but I do know that this is a Carnot. This is a Carnot device. This is a Carnot engine. So because it's a Carnot engine, here's one of the first, well, here's one of my first thought process. Because it's a Carnot engine, I can use the Carnot temperature heat relationship, or basically QH over TH is equal to QC over TC. This is, again, IFF means if and only if Carnot, and this is a Carnot device, so I get to use that. So I'm thinking that's got to be helpful because I don't know anything about heat, but I do know something about temperature. So this number 3 does let me relate heat with temperature. There is a linkage between input heat and waste heat with the input heat's temperature, the temperature at which that input heat was fed to the engine, and the temperature at which this rejected heat was the temperature of the reservoir into which the rejected heat flowed. Okay, so that I'm thinking that, the other thing I am thinking of is this, because how do I take advantage of work? How do I somehow tap in to that number? Because to be quite honest, I'm thinking it's time to live in the numerical world versus just the big picture conceptual setup, which is obviously has to come first. But I'm going to think efficiency. Carnot efficiency is what you want. What do you want? I want my Carnot engine to do work. How are you going to pay for it? What you pay. I'm going to pay for it in the form of heat dollars, what you pay. So that's generally what efficiency is. What do I want? I want work. How do I pay for it? QH. All right, so I'm thinking I'm going to start focusing on step 3 and step 4. This is efficiency right here. And this is my heat temperature relationship here. All right, so here goes. Let's just go on. Work here for Carnot. What is work? I guess I'll make this a separate line. Number 5. Let's use first law. Let's use first law. If I use first law on this engine, N equals out. N equals out. So what's coming into my engine? Hot heat. QH. I'm feeding my engine that. What's coming out of my engine? Work plus rejected heat or cold heat. All right, so I'm going to use the first law, number 6, update number 4. So here's my new and updated number 4. Number 4 now says efficiency equals work, and you can see work is going to be QH minus QC over QH. So again, maybe here I could have said, therefore, work equals QH minus QC. Okay. So that's efficiency. That's efficiency, generally speaking. But let's not forget, here's another expression for efficiency. Well, I'm going to go, this equals, I guess, I'm going to leave it like that, I guess. Now I'm going to combine, I'm going to splice in number 3. Okay. So from number 3, you can see from number 3, what should I'm going to just say QC. If I just do a little algebra step on step 3, QC equals TC over TH times QH. So again, that's what I did. Just a little sidebar conversation. This is always true if it's a Carnot device. Live through that derivation. So I'm going to take advantage of this expression for QC. So back to number 6 now. Efficiency is QH minus QC, and here's QC, TC over TH times QH. That's my numerator. Here's my denominator, QH. So just to reinforce this expression here, this is QC. That is in fact QC. So lots of stuff going on here, but you can see how that simplifies. This efficiency can be simplified down into, if I factor out all the QHs, 1 minus TC over TH. And I can write this. This is efficiency, and specifically, this is true for Carnot devices. It's not true for non-Carnot devices. This is a valid expression that we just derived. This is true if you're dealing with a Carnot device. And I'm feeling good now because I do know TC, that's given. I do know TH, that's given. And then I'm just going to go back to find an expression with QH. So check this out. I'm going to I guess I'll write down number 7. Number 7. Aha. Combine number 4. Number 4 and number 6. If I combine number 4 and number 6, I get step 8. Number 4 is work. Well, number 4 is efficiency in general is work over QH. That's true. That's always true. And specifically now I can say, well, specifically for this Carnot engine, efficiency is work over QH, but it's also 1 minus TC all over TH. And basically, I'm done because you know everything here except for the dollar signs. I know work. I know cold reservoir temperature, hot reservoir temperature. This is my dollar sign. So let me stick with you just for another couple steps. Step number 9 says, solve for QH, sorry. Let me do this. Let me call this step 9, solve for QH. So if I solve for QH, let me switch colors too. If I solve for QH, step 10, QH, and this is for 1 second, QH equals work, which I have a number on that, all over 1 minus TC, and I got to convert from Celsius to Kelvin, over TH. So let's get a number on that right now. Work 513 divided by 1 minus TC, 44.1 plus 273 divided by QH, 115 plus 273. Okay, I get 2807.39 joules in 1 second. 2807 joules in 1 second. So if I have 2,807 joules in 1 second, that's the same as 2,807.39 watts. That's how much heat. That's the rate. This is the rate at which I need to feed my engine. This is my feeding rate. I need to maintain this feeding rate. Maintain this feeding rate to constantly produce 513 joules of work. Okay, done with part A. Part B is just algebra, so let me zoom out. There's nothing new to say about part B other than algebra. So different color again. Part B, we're looking for Q sub C, and then this will be a job for the first law. Use first law. And we're done. If we use the first law, this is step 11. First law basically says one way to state the first law is in equals out. And don't forget, the other way to state the first law is change in internal energy equals Q minus W. That's true too. In fact, we could use either of those, but whatever way you use, let's just go back. What's in Q sub H? Whatever goes in must come out. What's coming out? Work plus Q sub C. Number 14, solve for Q sub C. And it'll be the same. So when I do that, I already have Q sub H. I'm going to subtract work, and I get 2294 and some change. And that's in 1 second. Q sub C equals 2294 joules in 1 second. Also known as 2294 watts. That's it. That's the rate at which, and then again, think like an enlightened citizen and ask yourself, how can I reclaim this heat? I mean, if you're an automotive manufacturer, you're going to use this heat for this heat comes from braking. You slam on the brakes, you generate all that heat, you send all of that heat back into a generator or a thermoelectric device, and you basically you need to figure out how to reclaim this heat and get this heat to do some more work for you before you call it quits. All right, that's it. That's chapter 20, quiz 5. Time check. It's now, it's 11:07. Let me just do a quick look ahead. What does number 6 look like? Yikes. All right, so I think, you know what? 6, 7, that's not going to happen. 8, 9. We'll do one more quiz. We'll do quiz number 9 because that can go pretty quickly. Okay, I'll leave this up. So we're going to go out of order. I'm going to go from chapter 20, quiz 5 to chapter 20, quiz 9. So we know to expect that out of order sequencing. Give me a minute to get that ready. Chapter 20, quiz 9. All right. Chapter 20, quiz 9. Our last quiz for today is now available. Chapter 20, quiz 9. Yes, out of sequence. There's lots of deep dives. Don't forget about the deep dives. Chapter 20, quiz 9. Seems to be brief. This corresponds to your homework, chapter 20, problem 44. In your homework, you should not only get this quiz correct, but finish that homework problem today or tomorrow. I'm not saying spend more time. I'm just saying spend your time, invest your time earlier. You need to figure out how much time you need to spend. I'm just saying, whatever time you spend it sooner. Spend it as far away from the deadline as possible. All right, so it's a Carnot engine. Ooh, this is during each cycle. So it's an engine that's made, because I kind of forget what I'm reading here. Let's see. All right. During each cycle, a Carnot engine absorbs 751 joules as heat. So again, let's draw the basic picture for engines. Vertical line, horizontal line, vertical line. What do engines do? Engines take hot heat from some source, like an explosion, at some high reservoir temperature. So hence the arrow like that. Engines do work. That's why we have engines. And there's always some amount of waste heat, Q subscript C, expelled to a cold reservoir at some temperature T sub C. During each cycle, a Carnot engine absorbs 751 joules from a high temperature reservoir. So this is 751 joules of input heat from, again, you burn something, or you tap into a natural source of heat, like a volcano, literally. And this hot reservoir is 376 K, so we don't have to worry about conversions. With the low temperature reservoir at 282 joules, I guess that's it. During each cycle, a Carnot engine absorbs a bunch of heat, 751 joules at 376 Kelvin, with the low temperature reservoir at 282 joules. How much work is done per cycle? Let's do that. Ready? In equals out. In equals out. In equals out means my input heat, Q sub H, must equal the output energy, work, plus Q sub C. And part A says how much work is done per cycle. So then we could say work is Q sub H minus Q sub C, or 751 joules minus 200. Minus Q sub C. I got it back. I got ahead of myself. But this is true. So that's step one. Step two. Number two, what's Q sub C? What's Q sub C? Okay. The answer is I don't know. So I'm going to once again use the Carnot temperature. I think it's heat temperature relationship. This is a Carnot device. This derivation is well worth it. Can't wait to see how much you enjoy this derivation, specifically QH over TH equals QC. You can't use this unless it's a Carnot device. And that's a mistake. That's a mistake that's often made. So from here, you can see that work, am I after, no, I'm not after work, but I'm after Q sub C. Q sub C equals TC over TH times QH. Okay, so now let's update number one again. Number 5 says, let's redo number one. Number one is saying work equals QH minus QC, and here's QC. QC is TC over TH times QH. Or I guess we could say, if we factor out a common term, QH times 1 minus TC over TH. That is work. Unless I made a mistake somewhere. Let's see if this works. Q sub H is 751 times 1 minus 282 divided by 376. Okay. This is the amount of work done. 187.75 joules. And I need to make a little typo. So typo alert. Just caught my eye. This should be not joules, but Kelvin. So typo 282 Kelvin. Because that was screwing me up. That's part A. Part B is the engine is then made to work in reverse to function as a Carnot refrigerator between these same two reservoirs. So now everything's going to stay the same except for the following. The arrows reverse. How much work? Right. So I need to do some erasing. I'm going to erase this arrowhead and this arrowhead and this arrowhead because now this is a fridge. This is a refrigerator. This is a Carnot refrigerator. Fridge. So what do you want a refrigerator to do? You want a refrigerator to keep things cold. So now my arrowhead is going to go that way, this way, and that way. So what does a fridge do? A fridge finds heat, Q sub C, in an already cold reservoir or in an already cold area, in an already cold region, the cold reservoir, and pumps it out to a hot reservoir. That's what refrigerators do, to a hot reservoir. Where is the hot reservoir? In terms of just walk into your kitchen, look at the refrigerator in your kitchen and ask yourself, where's the hot reservoir? And it's basically the area between your refrigerator and the wall. You ever put you drop something, you drop a pen behind your refrigerator and you reach in and you notice it's quite warm back there. That's the hot reservoir. This is what a refrigerator does. This work is needed. I need to invest. I need to invest work. I'm not getting work out of a refrigerator. I need to invest work, which is basically energy. I need to invest energy to make this happen. Because heat never naturally flows from cold to hot. Heat naturally flows from hot to cold. So I need to make this special investment. And then this is the area where fridge heat gets spit out. Gets spit out too. Okay, so this is a heat engine in reverse. Okay, so it says now we're running like a refrigerator. It's the same two temperature reservoirs. Okay, so I'm going to erase this because this is no longer applicable here. I don't know. There is no input heat. There's waste heat or heat Q sub H. Right. So there you go. During each cycle, how much work is required to remove this amount of heat from the low temperature reservoir? So this is Q sub H. That's Q sub H. Okay. So number 6. Number 6 says, well, I'm after work. I'm going to do again the N equals out. But now I have what's going in. I have QC plus work are going in. What equals out? Q sub H. So there's my dollar sign. Let's see. I do know Q sub, I don't know Q sub C. In fact, I don't know anything here. So I spoke too soon. Let's keep going. number 7. Well, I can say this. Work equals Q sub H minus Q sub C. And I do know Q sub C. So let me mark that down. I do know Q sub H. During each cycle, how much work is required to remove? How much cycle is required to remove 1213 joules as heat from the load? So that's a typo. This is why it pays to read the question a bunch of times. How much work is required to remove 1213 joules as heat from the low temperature reservoir? So literally, that is quite directly saying this is Q sub C. That's Q sub C. So I do know Q sub C, but I don't know Q sub H. So let's do the Carnot heat temperature relationship one more time, which basically says QH over TH. I know TH equals QC. I know QC over TC. So that is, once again, the Carnot heat temperature relationship. Okay, so work, I'm going to, I guess, talk about efficiency. Let's see, number 8. So therefore, work equals Q sub H. Equals Q sub H. Before I do that, let me go back to number 5. So I'm just going to say Q sub H equals TH over TC times QC. All right, so that's true. And let me just insert a comment here. Revisit number 7, and this is step 9. Okay, 7, 8, 9. Revisit number 7. So if I revisit number 7, work equals QH, and here's QH, TH over TC times QC minus QC. And you're done. Number 10, done. You know all of that stuff. So let's just, same reservoirs, hot temperature 376 divided by 282 times QC. QC is 1213 minus 1213. Okay. This is how much work you need to do to maintain these fridge temperatures, 404.33 joules. That's the answer to B. We are completely done, and it's 11. We're done early. It just doesn't seem right to finish this early, but let me look at, you guys can still, let me get a feel for everything. All right, so chapter 20. Okay, let me interrupt you for a minute so you can let me know.